General relativity suggests the fabric of spacetime contains a unique loophole. It can expand and contract faster than the speed of light. This visualization illustrates the Alcubierre metric, a theory proposed in 1994. It demonstrates how a drive could manipulate the local grid, contracting space in front of a ship and expanding space behind it, bypassing the universal speed limit without violating Einstein's laws. While the math holds up, the engineering requires a massive quantity of negative energy, a phenomenon we can only produce at microscopic scales, far below what is needed to warp space. For decades, researchers have been stalled by this energy barrier. We have exhausted our ability to test these limits manually, leaving physicists staring at the same complex equations on chalkboards without a path to a physical prototype. The sheer complexity of these equations creates a second bottleneck. Before we can solve the energy problem, we need to iterate through millions of mathematical configurations to find a more efficient model, a task that exceeds the capacity of a human lifetime. Artificial intelligence fills this gap. It simulates millions of complex physical systems simultaneously, testing hypotheses and identifying patterns in the Alcubierre metric that would take a human team decades to uncover. These models are effectively compressing centuries of manual trial and error into seconds of calculation, accelerating our progress toward the physical limits of the universe. This diagram shows an AI-derived breakthrough, a stable, segmented field of multiple distortion regions. Inside, the ship remains stationary in a flat, undisturbed pocket, isolated from the violent perimeter. Like a surfer, space itself carries the craft forward on a continuous gravitational wave. This multi-region model drastically reduces the energy requirements calculated in the 90s. However, achieving these velocities creates a counterintuitive physical paradox for anyone inside the bubble. If a ship travels faster than the speed of light, light from the destination cannot physically reach the cockpit. As the space around the ship bends, the visual universe distorts and then vanishes. Standard sensors and the human eye lose the ability to perceive anything ahead until the view abruptly plunges into pitch blackness. This phenomenon is the blind horizon. At warp velocity, the target becomes invisible, making traditional navigation impossible. We are left with a contradiction. We have the theoretical speed to cross the universe, but we lose the ability to see where we are going the moment we engage the drive. Because the pilot cannot see through the blind horizon, their role inside the bubble is reduced to a passive observer, and AI becomes the sole navigator. Predictive neural networks calculate the journey, locking in a path through the void before reaching light speed. The system dynamically maps warped spacetime, adjusting for anomalies through pure calculation without requiring visual feedback. Without an AI overlaying its predictive math onto the darkness, the ship would be navigating a graveyard of gravitational hazards. This future of deep space travel requires a leap of pure math, shifting the focus of exploration from physical engineering to predictive algorithms. To survive the journey, human explorers will have to surrender their reliance on physical senses and trust the precision of the calculation. The Alcubierre metric remains mathematically consistent with general relativity, even as the engineering required to power it stays far beyond our current reach. AI is currently closing that gap by simulating the solutions we cannot yet build. When the moment comes to engage a warp drive, the transition will mark a total shift in human reliance, moving from the certainty of what we can see to the precision of what the math predicts. Research and curation for this episode was conducted by Jim Columbus, also known as ND Maverick, developed in collaboration with Notebook LM.